We've been afraid of the wrong thing. For decades, black holes have occupied the darkest corner of our cosmic imagination. Objects so dense, so gravitationally extreme that not even light can escape them. We treat them as the ultimate endpoint, the most destructive force the universe can produce. But there are objects out there that make a black hole look almost gentle. Objects that don't just trap light, they shred it. Objects that don't just destroy matter, they sterilize entire galaxies. Objects whose energy output in a single second exceeds what our sun will produce across its entire 10 billion year lifetime. And the most unsettling part? Some of them have already fired in our direction. I'm Captain Vega, and every time I think I've found the ceiling of cosmic violence, every time I think I understand what the universe is capable of, something like this appears and moves the ceiling somewhere I wasn't prepared for. Let's go find it. To understand what lies beyond black holes on the scale of cosmic destruction, you have to first understand what makes black holes so extreme, and then understand exactly where that extremity ends. A stellar mass black hole forms when a massive star exhausts its nuclear fuel and its core collapses under its own gravity. What remains is an object typically between 5 and 20 times the mass of our sun, compressed into a region perhaps 30 kilometers across. The gravitational field at its surface, the event horizon, is so intense that the escape velocity exceeds the speed of light. Nothing that crosses that boundary returns. That is genuinely terrifying, but it is, in a sense, a local threat.
A stellar mass black hole is gravitationally dominant only in its immediate vicinity. Get far enough away, and its gravity is simply the gravity of a star. Destructive up close, ignorable at distance. The objects I want to tell you about are not ignorable at distance. The first category that surpasses the black hole in raw destructive reach is the magnetar. And to understand what a magnetar actually is, you need to hold two numbers in your mind simultaneously, because the contrast between them is almost impossible to process. A magnetar is what remains after certain massive stars die. A neutron star, roughly 20 kilometers in diameter, containing more mass than our sun, 12 miles across, more mass than the sun. The density at its core is so extreme that individual protons and neutrons are crushed together into a continuous fluid of nuclear matter. A teaspoon of this material would weigh approximately 1 billion tons. That alone would qualify as one of the most extreme objects in the universe. But the magnetar's defining feature isn't its density. It's the magnetic field. A magnetar's magnetic field is approximately 1 quadrillion times stronger than Earth's, 1,000 trillion times. The number is so large it becomes almost meaningless until you consider what it does. At a distance of roughly 1,000 kilometers from a magnetar, roughly the distance from London to Madrid, its magnetic field would be strong enough to disrupt the electron orbitals in your body's atoms, not burn you, not crush you, fundamentally alter the quantum structure of your matter before you got anywhere near the surface. And at a distance of roughly 200,000 kilometers, less than the distance from Earth to the Moon, a magnetar's magnetic field distorts the vacuum of space itself. It creates a phenomenon called vacuum birefringence. Space-time behaves differently depending on the direction of light passing through it. The observation confirmed that magnetar fields are strong enough to alter the fundamental properties of empty space. And in 2004, a magnetar approximately 50,000 light-years away, on the other side of our own galaxy, released a burst of energy in a fraction of a second that briefly outshone everything else in the observable sky. The event lasted about 0.2 of a second. In that time, it released more energy than our sun emits in 250,000 years. The burst was strong enough to partially ionize Earth's upper atmosphere from the other side of the Milky Way.
Military satellites called Vela
which were designed to monitor Soviet nuclear tests from space. The satellites began detecting powerful bursts of gamma radiation, but they were coming from the wrong direction entirely, not from Earth, from deep space. The discovery was classified for years before being published in 1973 by Ray Klebesattel, Ian Strong, and Roy Olson. For the next 2 decades, the origin of gamma-ray bursts was one of the most contentious debates in astrophysics. Thousands of papers proposed explanations. The bursts lasted seconds, left no obvious remnant, and were distributed uniformly across the sky, suggesting cosmological distances, which meant their energy output was almost incomprehensibly large. The debate was formally dramatized in 1995 in what became known as the Great Debate on Gamma-ray Bursts, a direct reference to the 1920 debate about whether galaxies existed outside the Milky Way. The scientific community was genuinely split. The answer, when it came, required an instrument we hadn't built yet. In 1997, the Italian-Dutch BeppoSat satellite detected a gamma-ray burst and for the first time precisely located its X-ray afterglow within hours of the event. Ground-based telescopes then found an optical counterpart, a fading point of light that could be spectroscopically analyzed. The redshift of that light placed the burst at a distance of roughly 6 billion light-years. The energy calculation that followed was staggering. In approximately 40 seconds, this single event had released as much energy as the rest of the observable universe combined. The mechanism behind long gamma-ray bursts, those lasting more than 2 seconds, is now understood to involve the collapse of a massive, rapidly rotating star into a black hole. As the core collapses, 2 incredibly focused jets of gamma radiation and matter punch through the star's outer layers at near the speed of light. These jets are so concentrated that if one points toward Earth, we detect it from billions of light-years away. If it misses us, we never know it happened. Short gamma-ray bursts, lasting less than 2 seconds, appear to originate from the merger of 2 neutron stars. In 2017, the gravitational wave detector LIGO observed a neutron star merger simultaneously with a short gamma-ray burst and its optical counterpart, confirming what theorists had long suspected and opening an entirely new field of multi-messenger astronomy. And here is the question that I find genuinely difficult to put down. Could a gamma-ray burst affect Earth? The answer, based on current evidence, is yes, in principle. A gamma-ray burst directed at Earth from within a few thousand light-years could strip away the ozone layer, exposing the surface to lethal ultraviolet radiation from the sun. Some researchers have proposed that the Ordovician mass extinction, approximately 450 million years ago, which killed roughly 85% of marine species, may have been triggered by exactly this mechanism. The hypothesis is not proven, but it cannot be dismissed. What magnetars and gamma-ray bursts share, what makes them deadlier than a black hole in the way that matters most, is reach. A black hole destroys what falls into it.
A magnetar alters the fabric of space in its vicinity and occasionally detonates with enough energy to affect planets on the other side of a galaxy. A gamma-ray burst can sterilize a hemisphere of a planet from 10,000 light-years away. The universe doesn't reserve its most extreme violence for close range. The more I explore these objects, the more I think the word dangerous needs to be redefined at cosmic scale, not by proximity, by reach, by the sheer volume of space a single event can render uninhabitable in seconds. We live in a universe quiet enough for us to exist. That it is sometimes this violent, at these scales, at these distances, and we are still here to study it, is either extraordinary luck or evidence that we haven't understood quite how sheltered our corner of the cosmos actually is. Either way, I don't find that comforting. If the violent edge of the universe pulls at you the way it pulls at me, the next investigation follows directly from this one. Because the objects we've explored today were all born from something,
from the deaths of stars, from neutron star collisions, from the collapse of systems far more massive than anything in our solar neighborhood. And the star deaths that produce gamma-ray bursts are connected intimately to a class of explosion called hypernova, a collapse so extreme it makes an ordinary supernova look like a footnote. That investigation is already waiting, and I promise it goes somewhere even more extreme than this.